So I wanted to share what I've been doing for the last week or so, and that's been tensile testing some 3D printed parts in a very primitive do-it-yourself way. This all started about 5 years ago when I set up this test rig when I was at the makerspace at Freeman Library, and people were asking how strong 3D printed parts were, and so I put a hanging scale and some 3D printed parts in the turnbuckle and tightened up the turnbuckle until they broke, and we were finding these test samples would withstand 500, 600 pounds of tension. And then I put that away and never really made it back to it. I thought it would be fun to try looking at it again. Well, that scale was rusted up and the batteries corroded and I couldn't get it to work. But I opened it up and the load cells looked fine. So I took the load cell out and connected it up to an open scale board from SparkFun. Now this may not be the ideal board for this application, but the way I configured it, it can sample every 400 milliseconds, and that seems a little bit slow, but it worked well enough. I designed and printed a custom enclosure for the load cell, hooked it up to the open scale board, and then one of the disadvantages of doing it this way is I don't have a gauge factor for the load cell. I don't have temperature or humidity sensors on it, so it can go out of whack in calibration fairly easily. So before I use it each time, I actually hook it up to another hanging scale, put it under tension, load it up to 250 pounds or so, and calibrate the load scale like on the open scale board with the calibration tool that's available and the software there. So I needed some tension samples to break. This is the test coupon geometry that I started with, designed in Onshape. It has a 6mm square cross section at the neck, and one source had a published maximum tensile strength of 37 megapascals, and with a 6mm square cross section that would indicate a maximum load of around 300 pounds, which seemed about right for what I wanted to do. This is the orientation that the samples were printed in on the printer. They were printed out of inland PLA+. This is orange, but most of the test samples were printed black in the black color on an Ender 3 Pro printer. This is a cross-section view of what it looked like sliced. I used Kira 4.5.0 to slice them. They slice the STL. In this example, there's 4 walls with 40% cubic infill. At first I thought I'd be varying the infill to see how the various infill percentages affected the tensile strength, but as I thought about it, when you apply tension to this part, most of the load is actually going to be carried by the walls of that necked area. So actually what I did was vary the wall thickness and the number of walls to see how that affected the strength. And so there it is, loaded up on the rig. You can see the open scale board on the far right. The gray box is the load cell. The sample is in yellow. And then on the left is the turnbuckle, which gets tightened up to apply the load. And then here's an example. If I can get this to play. In slow motion, the turnbuckle gets tightened and the part fractures in different modes. As the part is under tension, the load cell is being measured by the open scale, and that's reporting to the computer, which is recording again every 400 milliseconds. You can see as the turnbuckle increases, the tension, and then I stop turning the turnbuckle, it relaxes it a little bit, so there's this sawtooth form. That relaxation is partly due to the elongation, the plasticity of the sample. There's also some elasticity in the test rig, but this is what the data looks like. And then the maximum load for each of these curves is what's reported as the maximum load strength prior to fracture for each sample. So this was done about 80 times, recorded for different wall thicknesses and different parameters. So after doing that a bunch of times, we have these parts that are broken. Many of them fractured as expected in the neck area. Some of them fractured along the perimeter where they delaminated. Most of the ones at low wall thicknesses fractured in the neck. But once we got to high wall thicknesses, and we were seeing failures at high loads up around 300 plus pounds, more delamination failures occurred. So I did look at some rudimentary finite element analysis, which isn't something I've done in many years, so this is pretty crude. Under static load on a monolithic piece, you would expect the stress to be concentrated in the neck, and that's what we see at the low failures, where the contribution of the wall thickness and the infill is probably about the same. But when the wall thickness gets very thick compared to the infill, the lower section is probably, the lower image is probably more indicative. This is a shelled example, and you can see up in the corners there are some stress concentrations, and that's probably where some delamination is occurring. Once the part delaminates out of those areas, the effective cross-section of the part decreases, and then when you have a failure. So that makes a little bit of sense. So I went back and reevaluated what the part geometry should look like and added extra fillets at those corners. So this is the so-called extra fillet geometry, but it maintains the 6mm square cross section. This is what it looks like once it's been sliced. This has 6 walls, but it maintains the 40% cubic infill. Once again, we see delamination failures. But again, this is at much higher loads, again close to 300 pounds of force to cause these failures. Finally, I decided just to go ahead and see what the strongest part I could make would be. And so this is at 8 walls, which pretty much covers the entire width of that 6mm. I used 4 top and bottom layers with a concentric pattern, so it follows the perimeter. I used 100% concentric infill, again to follow the perimeter, and a random Z-seam so that there wasn't a seam down the side that might be a potential weakness. And of those 3 samples, 1 broke in the middle in the fracture that I expected, and the other 2 had the delamination failures that we've seen before. But these were at higher, typically at higher loads than the other one. So there was an improvement, but the failure mechanism is still the same. So what does this all look like in a graph? The earlier lower wall thicknesses failed at 200, 250 pounds. Once we see 6 and 8 wall thickness parts, we're getting close to that 300 pound expected failure load. There's a lot of variation once we get to that area, because the failure mechanisms are a little bit different for each piece, each sample I put a plus or minus 5% error bar on. That's sort of a guess on my part. My feel is that it's actually less than that, but I wanted to be conservative. So this is what it looks like. With this test sample with a 6mm square cross section, I think it's fair to say that you can design a part that's going to hold at around 300 pounds, or maybe a little bit more. And there are a lot of variables that go into it, and a lot of variance in the data based on which failure mechanism shows up. So what's next? We can change the layer height and line width. Those were all printed at 0.2mm layer heights with a 0.4mm nozzle. If we increase the nozzle size, then the line widths can be increased and we'd have a greater cross section per line. That might help. We could increase the printing temperature perhaps to improve the bonding between the walls, between little perimeters. There might be a chance that you can investigate some alternative infills and settings to help bind the outer walls to the inside infill and help with delamination. But probably what's next for me is to stop this investigation for now and go back to printing protective equipment for the COVID-19 response that's going on right now. But I do welcome your questions, comments, and critiques as always. You can put them in the YouTube comments below, tweet me at pbfarrell, or leave me a message here on Facebook. So let me know what you think if you haven't fallen asleep yet, and I will talk to you later. Bye.